Hi there. The object of this demonstration is to use this FPGA module. This is a Spartan-3 module, and this is the JTAG programmer. So the object is to make a waveform generator, a pulse generator out of this, that I could observe the waveforms on my oscilloscope. So I'm going to write some VHDL code and load it into this device, and it provides some waveforms. It provides a 10,000 Hertz waveform, a 1000 Hertz waveform, a 100 Hertz waveform, and a 10 Hertz waveform. Now I had already loaded this program. Once you load the program into the onboard PROM, you push this nconfig switch, and that loads the program into the FPGA. Now this module has 4 user LEDs on it. So the first one I have here is running at 10,000 Hertz, so you don't see, no, not 10,000, it's 100 Hertz. So 100 Hertz is pretty fast, so you don't see any flickering. The next one is 10 Hertz. The next one is 1 Hertz, and the last one is 0.1 Hertz. So basically I'm generating 6 waveforms. I put together some VHDL code, which we'll go through shortly to show how that works. So I just wanted to show you the setup. So this has 2 USB interfaces that go into a computer here. I'm going to show you the computer right here. So those are the 2 USB interfaces. And I have a Dell computer here that I'm using, and it has Windows 7 Pro on it. I'm going to show you the monitor here. So this is the monitor with Windows 7 Pro on it, and so we're going to use this computer here, which is connected. Now one of the USBs is used to interface to the JTAG device to program it, and the second USB is used just to power the module. You can see the connector here. That's the power. It's 5 volts, but although this FPGA reduces it down to 3.2 volts, it needs the 5 volt power for this module. And this is the USB that's going into the JTAG programmer over here. So we'll go through the process of loading the VHDL code so you can see how that works.
Okay, we're going to now talk about the FPGA VHDL demo design objectives of this project. So first I wanted to talk about some of the acronyms used. FPGA is the Field Programmable Gate Array, and that's refers to the device, the type of device we're using. Years ago they had PALs and many other logic devices that eventually evolved to these huge field programmable gate arrays that make a lot of things in our life possible now that years ago we didn't have technology-wise. So VHDL is an acronym for Very High-Speed Integrated Circuit Hardware Description Language, and that's the name of the programming language we're going to use today that we'll go through to program this device. So anyway, for me as a hobbyist, I'm not a big business, so I can't afford to buy many tools, so I have to use what I could get a hold on. So I was trying to find a low-cost method. A low-cost method was needed to learn about VHDL, and FPGAs. So there are a lot of other languages and higher-order languages you could use, but I wanted to use VHDL, which is a very deterministic type of language. Many of the other ones aren't as deterministic and sometimes aren't as successful, so I like going to VHDL. Has a lot of flexibility. So we needed to find, I was trying to find a low-cost method, being a hobbyist, to do this, being I'm not a big business and couldn't afford to buy a lot of the software and the hardware to do this. So anyway, I bought the demonstration kit from Waveshare. So this was purchased and used in this demo. So this kit provides many modules and demonstrations. I don't believe you could buy this kit anymore, but if you get a hold of one, it's a good way to go. But I'm sure there are many out there now. This was designed many years ago, so it's probably most of the stuff on here is obsolete, but it's great for learning. So There are many other ones out there now that you can look at. So if you can't get this one, there are other ones you can use. So I use XILINX ISE version 12.2, which actually came with the WaveShare kit, and this has the iSIM simulator built into it. Now I believe this ISE is also obsolete and overcome by newer versions. So I believe you could load this from XILINX website, and I don't believe they charge anything for the license. You could get a free license from it possibly. So so even if you don't have a device to program, it has iSIM in it, which is great. So you could actually simulate any device, and that way you could get a feel for how this works. Even if you don't have a device, you can at least simulate it. So a Windows 7 PC was used, as ISE doesn't work that easy with Windows 10. So this was developed years ago when Windows 7 was the main operating system that people use. So Windows 10, they do have some versions that work in Windows 10. I know the final version they came up was, I believe, was 14.7, but it runs on a virtual machine, and that's not compatible with the JTAG programmer. So that's why I stuck with Windows 7 for this project. So our design objective in this project is we're going to make a waveform generator out of the FPGA. So it's going to provide 6 waveforms. So it's going to provide a 10,000 hertz, a 1,000 hertz, a 100 hertz, a 10 hertz, a 1 hertz, and a 0.1 hertz. And one of the requirements is it has a 50% duty cycle, so it's on half the time and off half the time. And we're going to look at this. This is a good tool for my oscilloscope, so I could see how good my oscilloscope is reading these type of signals. It makes a little handy tool that I could use to help calibrate my oscilloscope or verify that my oscilloscope is working properly. So what I did is I programmed, wrote some VHDL code just to generate these waveforms that I could look at on oscilloscope. It's a good simple example to do if you're trying to learn how to do VHDL programming and try to go through the process of loading the code. It's not really code, the logic into the FPGA. So the difference between this and regular programming and regular software, everything is sequential, where everything runs one instruction at a time, where an FPGA, everything runs at the same time. There's a lot of parallel processing going on. So that's what makes it a lot different. So you have to think a little bit different when you program FPGAs, because everything is happening at the same time. You can make things sequential in FPGAs also, but generally the logic all runs at the same time. So like the end of the program could run before the beginning, and that's where you could get screwed up if you're used to programming in regular microprocessors or microcontrollers. So this is a little block diagram here now of what this module is. So the main part is our XILINX Spartan-3E FPGA, and here's the part number. So this is a pretty good size FPGA. It has 500,000 system gates. Of course, now these days they have ones that are humongous, that are much bigger than this. And now at the time, this was probably the state of the art. So this has 208 pins on it. So in this example, we're going to generate these 6 waveforms, or just pulses that I could use to observe on the oscilloscope. Now, this is a module, and actually has 4 LEDs on it also that you could utilize. So I tied the 100 hertz, the 10 hertz, the 1 hertz, and the 0.1 hertz to the 4 LEDs, so I could see them flicker on the device. So this module also has an XCF04S PROM. It's 4 megabits, and that's called the configuration memory. And when we power up the FPGA, this loads into the FPGA to configure it so that it has the program in it that loads. A lot of the newer FPGAs have this built into it, but at this point, they didn't do it that way, so they had a separate PROM. I guess in that way you could have different PROMs to load the same FPGA. And this is all JTAG, so you program it using a JTAG programmer. And this also has a 50 megahertz clock. This is kind of represents the module that core is on. Okay, I'd like to go through the process of showing you how to program an FPGA using VHDL. So we start off with only two files. One's a .vhd file that has the VHDL code in it, and the other one is a UCF file, and this provides links between the pins and the signal names. So we'll go take a look at these two files right now. So we'll open up the VHDL file and briefly take a quick look at it, and we'll start at the top here. And so we have the names of our input and output signals relative to pins, and these are our internal signals. So in this project, what we're trying to do is make a waveform generator that provides 6 pulse waveforms. One of them would be a 10,000 hertz output, and the next one would be 1,000 hertz output. The next one would be 100 hertz output. The next one would be a 10 hertz output. The next one would be a 1 hertz output. And the next one, the last one here, is a 0.1 hertz output. And all these have a duty cycle of 50%. So using logic, using VHDL, it's a pretty simple thing to do. This is all the code here. It's 247 lines. So it's not that big of the code to do this. So the other file that you need to write, this one's called SIG02. The second file you need to write is something to tell the system how to tie the input and output signals to the pins on the device. So this UCF file is the file that's used to do that. So as you can see, like these names, like LED01 is tied to pin 89 on FPGA. So we have LED1. So that tells the system what names to use and how they're tied to the pins. Now this module has 4 LEDs in it, and so LED01 we're going to tie to the 100 hertz flasher, the 100 hertz waveform, and LED2 we're going to tie to the 10 hertz, LED3 we're tying to the 1 hertz, and LED4 we're tying to the 0.1 hertz. So the object is to generate these 6 waveforms that I can look at on the oscilloscope and test it and show, yeah, that this device does put out these waveforms. So that's the code files. So from these two files, the system is going to generate a lot of files to do the synthesis and the program file and also the simulation, which we'll go through shortly. So one thing I wanted to check, I have the device connected to my computer. There's 2 USB connectors. One provides the 5-volt power to the module, and the other one is the interface to the JTAG programmer. So one other important thing to check is just to make sure that in our device manager that we're talking to the JTAG programmer. So I'm going to look at the device manager here, and so over here where it says programming cables, I want to see the XILINX USB cable, and that tells me that that driver is good going to the JTAG interface. So anyway, we're going to get started with ISE over here. So this is the ISE Design Suite version 12.2, and I'm using Windows 7 Pro. So I'm going to open that up now. So I'm going to close the last project here. So I go to File, Close Project, and I'm going to start a new project. So the new project is called SIG02. I generally try to keep the file names the same, with the same beginning at least, so that everything will match up for each of these projects. So I type SIG02 here with the name, and this is the path that was going to that directory that we just saw. This is the directory again. So you want to make sure that path matches with this path. So I'm going to hit next. on a new project wizard. So in here, this is the project settings, and this is the processor, the FPGA that I'm using. So it's a Spartan-3E, and the device is XC3S500E, and it's the 208-pin package, and the preferred language is VHDL. So we also have a simulator and the synthesis tool. The simulator is called iSIM. So we're going to run the simulator first just to make sure that our there isn't any type of errors, that it gives us some confidence that this device is going to work. So we hit next here. So this is just a project summary. So I'm going to hit finish here. So up here, you can see the part name. That's the part of the FPGA part number. So I'm going to click on here, and I'm going to add a source, which is the VHDL code. So that was the name of the file, sig2.vhd. So I'm going to attach that. And now I have to attach the UCF file. So that's sig2.ucf. So I attach that to the VHDL file. So I hit OK there. So if I open this up, you could see the hierarchy here that it has a part. This is the project name, the part number of the FPGA. This is the VHDL file, and this is the file that tells you how to connect the VHDL code to the input and output signals. So the first thing I'm going to do here is simulate this. So just to give me some good confidence that the device works. I'm going to so before we're in implementation, now we want to go to simulation. So I click on the VHDL code and highlight that, and then under here it says iSIM simulator. I'm going to open that up, and I'm just going to first do this behavioral check the syntax. So let that run. So I got that the syntax completed successfully here. So that's a good sign. So now I'm going to run the simulation. So I click simulate behavioral model. So it's going to open up the iSIM simulator now. So the first thing I'm going to do is restart it, because it defaults to give you a 1 microsecond run. And there's really only two inputs, the reset and the clock, that I could force. Now you can, another way of doing it is to make a special build of VHDL code that has that you can use for the simulation that sets all the inputs. But in this case, there's only two. If you have a lot of inputs, I would suggest doing that. But since this only has two inputs, I could force them to run the simulation. So I want to set my reset. I'm going to highlight reset here, the signal. So I'm going to force this to just a 1. So that means it's not in the reset mode. So I'm going to hit force the value to 1. So I'm forcing the selected signal to a constant of 1. So that means the reset isn't being pushed. When the reset's pushed, it's a 0. And when it's not, it's a 1. So the next thing is to force the clock. So this is a 50 megahertz clock that's in this on this FPGA. So I'm going to highlight clock and then click on this force clock. So I wanted to put out a sequence of 0 to 1, and the period is 0.02 microseconds, and that's 50 megahertz. Okay, that's equivalent to 50 megahertz. So I'm going to hit OK there. So I'm going to set the time now to 1 second. Let this run for 1 second. That'll at least run the 1 hertz. I'll be able to see the 1 hertz pulse. The 0.1 hertz pulse I'm not going to be able to see, but I'm going to launch this. So I just hit this arrow here. So the simulation is running. It's up to about 60 milliseconds now, and I need to get to the 1 second, which is 1,000 milliseconds. So the simulation's running. For this simple system, it's going to run pretty fast. If you have a more complicated system, yeah, the simulator could be slow, but I found this iSIM simulator to be pretty fast. It has a 1 picofarad frame that it defaults to, which is pretty good for most FPGAs that are that use 50 megahertz or 100 megahertz clocks. So this is almost done. We're up to 900 milliseconds, and okay, so it's done. So the first thing I want to do is just zoom to look at all the data. So this is our clock here. Maybe the first thing to do is zoom in on our 50 megahertz main clock. So you hit this plus sign here to zoom in. So you just keep clicking. So you could see the clock here. So this is our clock. That was forced by I used the forced clock. So now I'm going to check our 6 outputs. So the 10,000 hertz, let's see if this looks like a nice reasonable output. So I'm going to zoom back out. So you can see this is our it snaps on the transition. So you could actually use this to go to each transition, and you can use the cursors to measure it. So this is our well, I want to check our 10,000 hertz clock first. So I'm going to zoom in on that. So this waveform here is our 10,000 hertz clock, and as you can see, there's a 1,000 hertz clock. That's 1/10 of that, and then we have our 100 hertz clock. So let's zoom a little bit more out to see how that might look. So this is our 1,000 hertz, and I'm going to move back here a little bit. So you notice the 100 hertz output is using the 1,000 hertz. So it's got like a little delay, like when this waveform comes down, then this one comes up. So that's the implementation. There's of course many different ways you could implement it. This was a simple way. So it's looking at it's triggering off the 1,000 hertz to generate the 100 hertz. So this waveform here is the 100 hertz waveform, and likewise we're going to look at the 10 hertz one. So we're going to zoom, and this is the 10 hertz one here. So we'll move back here a little bit, and likewise, yeah, it's very similar. It's actually the same structure to the code, except it's the signal names are different. So this is our 10 hertz one. Now we're going to look at our 1 hertz. So we have to zoom all the way out here. In fact, we'll look at the whole thing. So we can only get like one cycle here for the 1 hertz, and the 0.1 hertz we didn't get anything. We'd have to run this for 10 seconds, and that could take a long time. So not going to do that. We'll skip that for now. So these are all our other intermediate signals that you can look at and analyze, and this simulator is very helpful for troubleshooting. So you want to make sure you simulate it first before you even attempt to program it, to make sure it looks pretty reasonable. So now we're going to get out of our simulator here. So I'll exit out of that. Now we're done the simulation part. So now we'll go back to implementation. So we're going back to implementation. So the first thing we want to do is our synthesis. So it's good to look at this console. This is the console output. So to synthesize it, to do the synthesis part, that's going to take the VHDL code and put it in some form that the FPGA could use to implement the design. So we'll double click on this. Sometimes this is where it fails if there's not enough gates. This system has 500,000 gates. So in this simple case, it shouldn't be an issue. So we'll double click on synthesize. So now it's going through the simple synthesize process. And this is a pretty simple one. So it did the synthesis and it completed successfully, and it gives you a lot of stats, things, how many flip-flops, and if you dig into the data sheet and dig into it, it's only using like 5% of the implementation of this FPGA. So this is a pretty simple design here. So now we're going to do the implement. So that does implement design. So that does like all the routing for this particular FPGA. So we got the check mark for synthesize. So now we want to do implement. So we'll double click that. And sometimes that could take a little bit longer. So it's generating all the files to implement the design. So it says global placement. So it's going to do a lot of routing and it's starting the router now. So it's doing that, and it does go through all these different phases and sequences. That's why some of these software applications are so expensive. The time it went into to figure out how to do this. But we're not worried about that. We just want to go from our VHDL code to make the processor work. So we got a good check on implement design. So the next thing to do is generate the programming file. So that takes just implement design files and makes a programming file out of it that you can use to download into the memory, into the PROM that loads the FPGA. So we'll double click on that. So generally this doesn't take very long. So that completed successfully. Okay, so the next thing we want to do is we want to program our target device. So this target device is currently connected up and ready to go. So we want to generate the target PROM. So there's a PROM on this module. It's a 4 megabit PROM that's used when you start up the FPGA. It loads it, so it configures the FPGA every time you power it up. There's different types of FPGA. Some of them have this PROM built in. This one has it as a separate device. So we're going to double click on that. So now it runs this iMPAC, which is the program that's used to deal with the target. So we're going to open that up now and we'll maximize that. So the first thing we want to do is create the PROM file. So this process, although it seems very complicated, it's actually not as bad as some of the other ones I've seen. And it's pretty straightforward using this ISE method. Of course, they probably have better methods now. So we want to double click on this create PROM file. So it comes up, and this is our PROM file formatter. So we want the XILINX flash PROM. So we want to click over here, and we have to select our PROM. So it's our PROM is a XCF004. It's the 4 megabit one. So we hit add storage device. So now we want to go over here to generate the file. So we want to get into the directory that we're working from. Our working directory is SIG2. So we hit OK. So now we want to type the output file name is SIG02. So we hit OK there. So our PROM comes up, but we now have to add our device. So we hit OK. And it's this bit file. We want to highlight that bit file. And we don't want to add anything more. So we have our PROM feeding our device, our FPGA. So now we want to generate the file. Okay, so this is the file that's going to get loaded into this PROM. So we double click generate file. So it says generate success. Okay, so now this is a JTAG system, so we have to load it with the JTAG system. So now next thing we want to do is this boundary scan. So we double click on boundary scan, and now we want to right click and add a XILINX device. So the first thing we want to add is this BIT file. So that's our FPGA. And now we want to add, this is the actual process of the programming. So the next thing to add is our PROM. So we hit open, and we have to pick the prom again. It's this XCF04S. So we have our system. We're going to use JTAG to program it. So we want to click on this so that it's green. You see how that's green there? And now we're going to double click on program. So double click on that. So now it's actually going to load it through the JTAG programmer. So I hit OK here, and it's actually loading the program right now. These are the commands that come up as it's loading. So program's succeeded. So now we're done, and it's programmed. The program has been loaded into the prom. So the next thing to do is there's a little switch on a device called nconfig, and that'll when you push that, it'll load the memory into the device, so the device will start running. We'll show you that real shortly. So we're done now, so we can get out of this and close this file. We could end our we could exit out of ISE. And now we're complete.
So now I'm going to test the device on the oscilloscope. So I have the device hooked up to verify that the waveforms are correct. So this black wire is the ground, and this wire here going into this connector is a waveform generator. So by moving it to different pins on this connector, I could get one of each of the 6 different waveforms. Right now it's hooked up to the 10,000 hertz waveform. So now looking at the signal on the oscilloscope, I have it set up so you can see the first signal is 10,000 hertz as shown by the cursors here. Now I'm going to switch to the next signal, which should be 1,000 hertz, by moving the pin, and we could just verify that's 1,000 hertz. So we're going to go down to the next signal, and I have to change the scaling here on the horizontal axis. So there you go, there's our 1,000 hertz signal. I'm going to go to the next pin, and this is going to be our 100 hertz signal. So I'm going to change the horizontal scaling again, and now you can verify it's coming out as 100 hertz. I don't know if you can see it, but it's measuring the frequency. I have it triggered to the signal. The amplitude is the 3.2 volts approximately for the pulse. So the next signal we have is a 10 hertz signal. So we'll change the horizontal scaling again. And here's our 10 hertz signal. So all these signals look identical, except the horizontal scaling is changed on the oscilloscope. So now we're going to go to our 1 hertz signal and switch to that. And change our horizontal scaling. So for our 1 hertz signal, we have to wait a little bit. Don't know if the trigger will pick this up or not, but this should be our 1 hertz signal. Let's see if we can pick it up with the trigger. So this is free running. Maybe I actually have it on the 0.1 hertz. So let's see what happens. We'll look at that. And I believe this might be the 0.1 hertz signal. So as you get to a lower frequency, yeah, it takes a longer time to make a measurement. So yeah, we have to go down one more on the horizontal scaling for our 0.1 hertz to get a good 0.1 hertz measurement. So it could take a little time, but this is a 2-second per square horizontal setting. So see if our trigger could keep up with that. Then we'll go back and look at the 1 Hertz one. So anyway, you could see that this is 0.1 Hertz. So let's try to get back to the 1 Hertz signal. I believe I skipped a pin. And we'll push up our scaling here a little bit. So, okay, yeah, there's our 1 Hertz signal. So this verifies that the device works and it puts out the waveforms as we wanted in our VHDL code. Okay, I want to talk about the VHDL code that is used to provide this waveform generator. So first, there's some standard library declarations here that we normally use with VHDL. So this is the standard ones, IEEE ones that are up here. And the first part is this entity declaration. So this entity shows our ports, our inputs and outputs. So these are our inputs. We only have 2 inputs, and we have some outputs here. And these outputs are tied to pins. So these 2 inputs are the reset. The reset is when you push the button that provides a 0 when the button's pushed. When it's not in reset, then it's a 1. So you want to use the reset to set things to initial conditions when the reset is pushed. And the other input that we have here is our 50 megahertz clock. So the outputs are the waveforms. So we have a 10,000 hertz waveform with a 50% duty cycle, a 1000 hertz, a 100 hertz, a 10 hertz, a 1 hertz, and a 0.1 hertz. And then there's 4 LEDs on the module, and these are tied to the 100 hertz signal, which is this 100 hertz output, a 10 hertz signal, a 1 hertz, and a 0.1 hertz. So you use this entity command here to define your port of inputs and outputs. Over here is the beginning of the architectural behavior of the system, and there's some intermediate signals that aren't inputs or outputs, but they're signals that are used in the code. So these signals here are just pulses, so they don't have the 50% duty cycle. They just pulse at every 10,000 hertz and 1,000 hertz, 100 hertz, 10 hertz, 1 hertz. And then we have these countdown timers. These are countdown timers that are used. The one that's very high is this 10,000 hertz because our clock is 50 megahertz, so we have to divide approximately 5,000, while it's 4,999 when you include the 0. So it's 0 through 4,999. If you divide that by the 50 megahertz, that gives you the 10,000 hertz. So this is all handled by countdown timers. Then there's our outputs that have the 50% duty cycles, unlike these that pulse every 10,000 hertz or 1,000 hertz. The pulse is sustained here for half of the time of the cycle. So this is the beginning of our processes now. So the first process here, which is shown here, is the assignment of the LEDs to the module. So the inputs are the reset and the clock, the 50 megahertz clock. So when in a reset, we want to set all these LEDs to 1, which is off. So on the rising edge of the clock, so if we're in reset, we set the LEDs to 1, but on the rising edge of the clock, we do this assignment where we set the these duty cycle logics control the LEDs. So if the duty cycle is a 1, we set the LED to 0 for 100 hertz. And if it's not a 1, then it's 0. So then it sets to 1. So these if else end if statements are used to set these LEDs. This area over here provides the 10,000 hertz signal generator. So it does it by using a down counter. So in the reset mode, when in reset, we initialize the counter back to 4,999, and these are the pulse outputs, and the duty cycle outputs are set to 0.
But on the rising edge of the clock, if the counter is zero, is not equal to zero, the counter is not equal to zero, we count down. But if it's equal to zero, we set it back to 4,999. So this is a way to get the 10,000 hertz counter, the 10,000 hertz pulse from a 50 megahertz signal, which is the clock. So when the counter counts down to zero, we fire off this pulse. If it's not zero, then we set it to zero, the output of the pulse. Now we have this secondary condition here, which provides our duty cycle. So if the counter is less than 2500, it sets the waveform to 1, but when greater or equal to 2500, it sets it to 0. So this area here is where we assign the duty cycle pulse to the output. You never want to put the output here in the code. It's just the way these FPGAs work. You want to do it at the very end. You want to have like a secondary parameter that is worked on, but when it's a port signal, you want to assign it at the end. So now our 1000 hertz signal generator uses the 10,000 hertz pulse that was generated back here, and that's fed in. So when it's in a reset, it resets the counter to 9. So this counter only ranges from 0 to 9, which has 10 states. So if we're in a reset, we reset the counter. If we're not, else if, then we do our routine. We count down our 1000 hertz counter. If the counter is not equal to 0, we do a count down. If it is 0, then that's where we want to generate our pulse, and we reset the counter to 9. So this generates this freak 100 hertz, but the counter is equal to 0, sets to 1, otherwise it's 0. So this provides a pulse every 1000 hertz. And this is our duty cycle version of the signal, which allows the pulse to be sustained for half the time, and then clears it for half the time, and then our assignment's done here. So likewise, for our 100 hertz signal, we do the same thing, except we feed in the 1000 hertz to drive it. And for our 10 hertz signal generator, it's the same algorithm basically, but we take the 100 hertz and drive it and divide that by 10 to get our 10 hertz. And then likewise, for our 1 hertz, we take the 10 hertz waveform and we divide that by 10 to get our 1 hertz. And likewise, for our 0.1 hertz signal, we take our 1 hertz signal and divide that by 10. So these are frequency dividers basically. So that's the end of our code. So I wanted to go through the VHDL code one time to show you what that was like. Thanks for listening to this. I hope this has helped you if you have to program some VHDL code.